These are notes on oxidation numbers. We're going to do oxidation numbers before we start naming because we think that it's going to help you with naming our D block elements that have a little bit interesting characteristics to them. So what are oxidation numbers? These are very similar to charge, but what they do is they show electron distribution specifically within a compound. So there's some rules that you need to follow when doing oxidation numbers. Pure elements are always 0. These guys are always a 0 charge. The atom or the diatomic molecule is going to be neutral, so the charge on that atom is always going to be 0. F minus 1 is always a -1. It's the most electronegative. You learned that in the periodic trends unit. It's the biggest bully on the periodic table. It's the most electronegative. It's always a charge of -1. It's also in column 17, which is a halogen, and these guys are always going to have a -1 charge. And there's another rule down here in number 6, group 17, column is always a -1 charge. So fluorine is always going to be a -1 charge. Oxygen is almost always a -2. There are some caveats to that, exceptions. OF2, the oxygen is going to be a +2 charge. And then with H2O2, the oxygen is going to be a -1 charge. We will use the general rule a majority of the time and try to remind you of those exceptions if you need to apply them. Group 1, column 1A is a +1. We're going to use the general rule the majority of the time, and its hydrogen is mostly the +1. Hydrogen is an exception with a metal. NaH hydrogen would be a -1. And again, we're going to try to remind you if you need to identify the exception to the rule. Group 2, column 2A, these have 2 valence electrons, so the ion will be a +2, so our oxidation numbers will be a +2. Group 13 is column 3A. These have a +3 oxidation number. This column has 3 valence electrons, and the ion will be a +3. So hopefully you're seeing some correlation between the valence electrons and the ion charge and the oxidation number. Again, group 17. So these will help identify the charge and the electron distribution. So group 17, these are halogens. They have 7 valence electrons, so the ion will be a -1. When we look at oxidation numbers and totaling, we always want to look at the compound sum. Unless it's shown to us, like in a polyatomic ion, a compound sum is always going to be 0. All atoms are going to give or take electrons to, or share them to be able to be like a noble gas and be electrically neutral. And so electrons in a compound that's electrically neutral, the oxidation number sum is going to be 0. Polyatomic ions, these are going to have a charge, and you can find these charges and these ions on the table on the back of your periodic table. And SO4 - 2, for example, the total charge would be a -2. NO3 - 1, for example, the total charge would be a -1. So use your ion chart when dealing with polyatomic ions. Polyatomic, remember, means many atoms, and you do need to learn these names and these charges of these polyatomic ions to make your life easier when writing chemical formulas and when writing chemical reactions. So when dealing with oxidation numbers, we're going to use the rules for the above compounds for the elements that you know. So you're always going to start with the elements that you know, and then to determine an element in that compound that you don't know, you're going to determine Roman numerals, and we'll teach you a little bit more about that when we learn how to name. And then you're also just going to use process of elimination if you know one of the compounds and you only have 2 compounds, you know the other charge. And let's get to some examples. So in this, we're going to again use the rules for the compound. So we're going to identify the charge of the known elements first. So in our example here of these 2, nitrogen and oxygen, I know oxygen's a -2. Remember, we're going to use that general rule there. So it's in column 16, which makes it a -2 charge. And so I'm going to put the actual charge of the atom, or of the electron above. So right here it's a -2 charge on oxygen. And then I'm going to identify how many oxygens I have. So I have 4 oxygens. That's what that subscript is telling me. So my total charge in oxygen there is -2 times 4, which equals a -8. So my actual charge is a -2. My total charge is a -8 because I have 4 oxygen atoms. So then I know that the sum of my compound is 0 because there's no charge right here. For example, there's a charge right there, and we'll get to that example in a second, but it's frame of reference when I'm talking about no charge. So now, because the sum of the compound is 0, I need to identify that a negative 8 and a positive 8 would give that a 0 charge. And so I know that the total charge on this nitrogen atom in this compound is a positive 8. So now to figure out the actual charge of the nitrogen atom, I've got to identify that there are 2 nitrogen atoms, and I've got to say, okay, a positive 8 charge divided by 2 nitrogen atoms means that the nitrogen atom has a positive 4 charge. So that's the electron distribution within that compound, and those are the correct oxidation numbers. So let's do H3PO4. Sometimes we're going to do PO4 as an ion, and sometimes we're going to do these as separate elements. Because of that split line there, we're going to actually identify those elements' oxidation numbers separately. So the first thing that we're going to do is identify our known elements first, and I actually know 2, hydrogen and oxygen. I'm going to start with the hydrogen, and I know the charge on hydrogen is always a +1. I know that there are 3 hydrogens because of that subscript right there. 1 times 3 equals a positive 3. And then I know that oxygen's charge is a -2. And most of the time in a lot of these examples you're always going to know oxygen's charge. And I know that I have 4 oxygens, so I'm going to take a -2 times 4 equals a -8. Because there's no charge on the compound itself, we know that the compound sum is 0. Then what we can do is identify a positive 3 plus a value minus 8 is going to equal 0. That's going to help us figure out our total charge on this phosphorus there. And that answer is a positive 5. Because there's only 1 phosphorus atom there, the positive 5 goes up there, and that's my electron distribution of H3PO4, which is actually phosphoric acid. Let's move on to one with a charge. So our charge right here is showing us that it's the -1, so that's going to be our sum. And it's important that we need to identify that because that will help us with our electron distribution. So I know my charge is my sum is -1. I know between nitrogen and oxygen, here that my oxygen is a -2. I know that I have 3 of them, so my total charge on oxygen is -6. So then I've got to ask myself, what plus a -6? So what plus a -6 equals a -1? And that would be a positive 5. Because there's only 1 nitrogen atom, there's no superscript there, but it's or subscript there, but it's an assumed 1. Because there's no subscript there, I know that there's 1 there, so my actual charge on nitrogen is a +5. So there's my electron distribution in that ion. And I'm going to have you look at your ion chart on the back of your periodic table that you got to figure out what the name of that ion is. Alright, so let's do an example for 2 unknowns. So in this case, we don't know the iron because it's in the D block and there's no Roman numerals with it, and that goes along with our naming rules, and so we'll talk about those a little bit later. And we also don't know the phosphorus. A lot of times things in carbon's group and nitrogen's group are hard to figure out the electrons on because they're variable, and most of the time those things are going to form covalent bonds instead of ionic bonds. But we know oxygen, but that's not really going to help us because we have 2 unknowns. The thing that we do know is that this is an ion, it's a polyatomic ion, and it's phosphate, and we do know the charge of that total ion there, and that's what we're going to use. So we're going to circle our polyatomic ion, and then we're going to give the group the ion charge, and then determine the charge of the metal. So the first thing that we're going to do is circle our phosphate ion there, so that's telling us that that's my phosphate ion. And I'm going to identify my charge on the phosphate ion as a -3, and I got that from the back of the periodic table. And I know that there's only 1 of them because there's no parentheses and it's not telling me I have any extra. And then I've got a -3 times 1 is -3. I know the sum of my compound is 0. Because the sum of my compound is 0, I'm going to be able to figure out that what plus a -3 is going to equal 0. So I know a positive 3 plus a -3 is going to equal 0. There's only 1 iron there, so I know the charge on the iron atom is a +3. That's going to help us name it. We're going to learn how to name later, so don't worry about filling in the names yet. Alright, let's do one more with polyatomic example, Fe3PO42. So I'm going to circle my phosphate ion again, and again I know that that's a -3 charge. This time I have 2 of them though. That parentheses and subscript 2 is telling me that there's 2. So I'm going to go -3 times 2 is a -6. So I know the total charge on the phosphate ion is -6. I know my compound sum is 0. So that means that what plus a -6 equals 0? Well, that's a +6. Then I can identify that I have 3 iron atoms. So 6 divided by 3 is going to equal our charge on our iron atom. So that would be a +2 charge in that electron distribution oxidation number. So as you can see, iron can have multiple charges, +3 or +2, so that's why we will learn how to name those later, and the charge will help us with the name. So that's why we want to do oxidation numbers first. Thank you for taking these notes and coming ready to class, and we will practice the rest of these in class and check them in class. Thanks.